Hi there. Welcome to our Renaissance Society speaker series. Today, we are pleased to present Dr. Tom Suchanek, who is the former chair of our Forum Committee. Tom is a marine ecologist who has spent the last 40 years conducting research around the globe, primarily on environmental contaminants. For the past 20 of these years, he has been focusing on one of the greatest threats to human civilization, climate change caused by the most critical pollutant of all time, carbon dioxide, or CO2. Tom earned his PhD from the University of Washington in Seattle and has had three diverse careers. First, conducting research and teaching at UC Davis for 20 years. Second, with the U.S. Fish and Wildlife Service in Sacramento as director of their Environmental Contaminants Division. And third, with the U.S. Geological Survey, also in Sacramento, as their lead scientist and research manager. He also spent 7 years as the Western Regional Director of the National Institute for Global Environmental Change for the Department of Energy. Today, he will discuss some of the most critical aspects of climate change that are affecting coastal California and what each of us can do to help solve this dire global crisis. So take it away, Tom.
I appreciate that nice introduction. I'm going to share my screen now. Thanks everyone for joining. Today I will talk about climate change impacts on the California coast and beyond, and really try to address the urgency of how we can develop solutions to solve this problem and many others related to it. So today's goals, I hope to identify the root cause of this problem, specifically carbon emissions and primarily carbon dioxide. We'll talk about the impacts to the California coast and beyond. And then lastly, we'll talk about what are the solutions, past, present, and future. So it'll be basically three different sections to this talk today. So we really need to, if we want to do that, we really need to go back to the basics and understand from the beginning where we came to this problem. And the greenhouse effect is really where we start. We have the natural greenhouse effect here, which is where the sun beats down on the earth. Some of that heat from the sun is absorbed and some of it's radiated back out into space. But some of it is captured in the atmosphere by these three greenhouse gases: carbon dioxide, CO2, methane, CH4, and nitrous oxide, N2O. And they rise up to about 7 miles into the atmosphere, and they act as a blanket to keep the earth warm. And that's a natural process. We really want that to happen, but not too much. If we didn't have the natural greenhouse effect, our whole planet would be basically ice. So let's look at the human enhanced greenhouse effect. Same process, sun beats down on the earth, some of that heat is absorbed, some of it's radiated back out into space. However, as you can see in this reddish area, this accumulation of carbon dioxide and methane and nitrous oxide is much larger. And that traps more and more heat as we continue to produce carbon dioxide and all these other emissions that are trapping heat. So basically today, we're going to look at the greenhouse effect, how it creates global warming, and then how that drives climate change. We're going to focus primarily on carbon dioxide, since that's 83% of the problem that we have. And we'll talk about why that is. So fossil fuel emissions are responsible for about 94% of all the total carbon dioxide emissions from human sources. And that comes down to coal, which is about 42% of the problem, oil, 33% of the fossil fuels, and natural gas, 19%. There's actually another 6% that are involved in the production of cement, but it's more complicated, and I'm just going to leave that at 6% and not really get into it because it would take too much time. So the global community, everyone on the globe, has been emitting about over 100 million tons of carbon dioxide every day into the Earth's atmosphere. And that's about 43 billion tons a year. Now, for a gas, that's almost unbelievable that a gas could be that much weight and that much mass. But truly, we put out 43 billion tons a year into the atmosphere, the global community. Now, we'll talk about California in a little bit. So what about the CO2 emissions being emitted all the way through from around the Industrial Revolution, which started in the 1700s and into the 1800s? What happened then is these are billions of tons of carbon dioxide on the left, and time on the bottom. And we started burning coal first back in the 1700s, early 1800s, and that gray area is coal. And then in about the 1920s, we started to burn oil. We pumped oil out of the ground and started burning it. So that's a significant influence there. And then in the 1940s, 1950s, we started pumping natural gas, and that's about 19% of our problem. So you can see that the accumulative emissions are going up faster and faster and faster into what we call an exponential rise, and that's what's happening right now. So we really need to squash that and get back to where we were if we can. So there's over 100 million tons of carbon dioxide per day and 40 billion tons per year by the global community. So let's take a look at what's happening more locally. The US gas emissions, carbon dioxide primarily. If we look at the electric power, by producing electric power takes about 25%, or costs us about 25% of the emissions. About 24% of emissions are produced by industry, another 13% by commercial and residential places. Agriculture produces another 11% of the total, and transportation is about 27%. I'm not going to go over all of them, but most of these, in terms of California, as opposed to the United States, are pretty similar. Some of them are a little different. However, the main difference that we're looking at is the difference between transportation in the US, which is only 27%, and transportation in California, which is 41% of our emissions. So we really need to be cognizant and trying hard to lower that emission proportion of carbon dioxide by transportation and all of these other things as well. But basically, we want to focus on the difference between what's happening in the US and what's happening in California, because transportation is, the emissions that we have are caused by the fact that, number one, we're a bigger state, almost, biggest state, and also we have way more cars on the road all the time than any of the other states. So let's continue on. On the left is the concentration of carbon dioxide in the atmosphere, like we were talking about, and this is how much carbon dioxide was in the atmosphere for the last 1,000 years. So each one of these little dots represent a core sample that were taken from ice cores that have little tiny bubbles in them. And they actually measure, it's hard to believe that they measure the concentration of carbon dioxide in those tiny ice core bubbles. And so they measured back 1,000 years, and we've been bumping along at about 280 parts per million, all the way to the Industrial Revolution that we started talking about in about 1750 or 1800. And at that point, when we started burning coal, that started zooming up again in this exponential straight up fashion to where we are now at about 418 parts per million. That's not a special number. It just means it's going up really fast. So let's go back, instead of 1,000 years, let's go back 1,000,000 years. So again, carbon dioxide concentration in parts per million on the left, and time, the last 1,000,000 years on the bottom. That's years before 1950 here. And as we look through this, we see these up and down concentrations of carbon dioxide over the ages. And every time it dips down is an ice age, and this is an interglacial age. So ice age, ice age, ice age, ice age. And humans didn't start being aware of and they didn't even appear until 200,000 years ago. But even then, we're starting to produce carbon dioxide, but we went into another interglacial, then we went into another glacial period, and then starts the Industrial Revolution right here. And as soon as we get into the Industrial Revolution, we start burning coal, and that sent us straight up to the 418 where we are now, way more than carbon dioxide has ever been in the last millennia. So we have a problem here, runaway carbon dioxide. The problem with carbon dioxide in terms of a greenhouse gas is that it stays in the atmosphere for about 500 to 1,000 years. That's a real problem because we can't get it down. We have to do something different. And that's the main problem that we have, is that it's there for so long. So let's take a look at what we have here in terms of carbon dioxide increase, like we just saw. This is parts per million, same thing, 418. And the blue line is temperature increase. So temperature in the blue line follows pretty closely. It's not identical, but it follows pretty closely to the rise in carbon dioxide. So the more carbon dioxide we have, and the more blanket of greenhouse gases in the atmosphere, the hotter and hotter it gets. And we'll take another look at that in a different way. So here, this is the level when we started the Industrial Revolution. And here we've risen up to about 1.8 degrees Fahrenheit above where it was at the Industrial Revolution. So we know that we're getting hotter and hotter. We're trying to keep it down as much as we can. So the last time CO2 concentrations were this high that we're talking about, 418 parts per million, humans didn't even exist. That was 800,000 to 20 million years ago. And at that point, global temperatures were substantially higher. There was almost no ice on the planet. And sea level was, unfortunately, 100 feet higher than it is now. So think about how much this is tracking the concentration of carbon dioxide. So be aware that we could be headed in this direction. So let's use this little bathtub as a model of carbon dioxide. If this faucet is carbon dioxide pouring into the atmosphere, there's a very little going out, being removed, but about 25% is absorbed by plants. Of course, they do photosynthesis, so they need carbon dioxide, and 25% is absorbed by the oceans, and about 50% remains in the atmosphere. That's the big problem. The plants take out about 25%. Originally, or quite a while ago, the Amazon actually took out about 5% of that. So they were doing really well. However, unfortunately now, Bolsonaro, the president of Brazil, has started wiping out part of the Amazon to grow cattle for hamburgers and other types of crops other than the tropical rainforest trees. So we can't rely on the rainforest to really take out 5% anymore. So let's take a look at the air temperature increase that we've seen. So here's the last 10 years of global temperature. And if we look at the last six years were the hottest years on record. And if we think back, we started getting rolling blackouts around 2019, 2016, 2019 especially. Now, if we add the data from 2020 into this mix, we then see the last 7 were the hottest years on record. So we're getting hotter and hotter or staying hotter. Let's add 2021 to this mix. So if we do that, now the last 8 years are the hottest years. This one is very close to 2018, but it's still among the hottest 8 years ever that we experienced. So the reason this went down somewhat is because that particular year, last year, was a La Nina year, and that pulled up really cold water from the deep ocean, which cooled things off a bit. So I'm sure that you may have seen this. This was last summer, 2021. British Columbia got up to 121.6 degrees Fahrenheit. And I don't need to tell you what's been happening in the last month or two. All of you, I'm sure, have been suffering the heat in the West and everywhere on the globe for that matter. It's really been baking out there and breaking records all the time. So we need to take a look at these and see what's happening. So let's take a look at the ocean temperature, similar to the air temperature. Again, the heat content over here. And as we go from 1955 on to the present day, over the last 75 years, we can see there's 4 different measuring groups, researchers, that all produce basically the same kind of information. The ocean temperature is getting warmer and warmer all the time. Remember, 50% of it is being stored in the ocean. The other concern that we have with the ocean heating up is methane, and specifically methane ice. This is a chunk of methane ice. And remember, methane is 20 to 80 times more powerful than carbon dioxide. And that's bad, but the good part about it is that methane only lasts in the atmosphere about 10 to 12 years, as opposed to the 500 to 1,000 years for carbon dioxide. But when it's first released into the atmosphere, it's way more powerful and way more destructive than carbon dioxide. So here we have sea level. We have this zone near the coast, which is a zone of gas hydrates, which are basically broken down organic material falling off the coast and being absorbed into about the top 20 meters down there. This is about 2,000 meters deep, And these the cold areas down there, the freezing areas, 1 or 2 degrees, freeze this methane and put it into an ice form. Now, what happens, and what we expect to be happening if we go too far, is that this methane will start melting because the ocean temperature is getting hotter and hotter, all the way down here into this zone of methane ice. If that happens, the methane is going to go up into the atmosphere. Again, it's 20 to 80 times more powerful. And we may actually hit a place where we have a global tipping point. And we can't put the toothpaste back in the toothpaste tube, and we can't put the methane back into ice very quickly because the ocean is going to be so warm. So that may present a really, really sobering picture if that happens. So let's talk about the next impact that we see in the coastal ocean of California and elsewhere. These are calving glaciers in Alaska. And here's sea level rise. Lots of different processes at work that control the sea level rise. And I won't go over all of them, but I'll just say, basically, we have about 50% of the sea level rise coming from the melting of glaciers and ice caps. Another 50% from seawater expansion. Now, you may not think that water getting warmer is going to expand that much, but it really does. This is huge in terms of the sea level rise. And finally, another 50%. Oh, wait a minute. No, that's not right. Forget that. Let's go on to the Greenland ice sheets. This is from 2002. This is the level that the ice sheets were at that time. This is the monthly change in ice sheet mass on the left over time, starting in 2002. And you can see that the ice is going down, 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 down on the ice sheets. I was almost in Greenland this past summer and got COVID and wasn't able to go. So I wanted to see the ice sheets in Greenland before they disappeared, but I guess I'll have to make a special trip for that. In July of 2019, the melting Greenland ice sheet poured 197 billion tons of water into the North Atlantic in July alone. And that's all contributing to the sea level rise issues. So let's look at the global sea level rise. And here's the Industrial Revolution just before 1800s. This is the change in sea level compared to an average. And here it is, 1880, when basically right after the Industrial Revolution started, going up and up and up and up and up until we reached 2020. And you can see that's just getting almost going to an exponential point. The global mean sea level has risen about 8 or 9 inches since 1880. And more recently, since 1993, they set a new record high of 3.6 inches in that period of time. So it's going higher and higher and faster and higher. So there have been some estimates of global sea level rise by the National Research Council, and they estimated how much is the sea level going to rise in the year 2030, by the year 2050, and by the year 2100. And they did that for a number of locations: Washington and Oregon, California, and then there's a couple of other reports here. But keep your eyes on California. So their predictions and their estimates of sea level rise in California are about 30 centimeters, but that's equivalent to about 0.8 feet. By the time we reach 2050, California will have risen up to 2 feet. And by 2100, we have a range here, but we could be reaching 5 feet by that time. So notice that California is really the highest projected sea level rise for all of these places. And we're going to be experiencing that before too long. So get out your kayaks. So let's take a closer look at some of the areas around us. Basically, the ocean is not a flat surface, and we, especially in bays and in estuaries. So if we look at Puget Sound up here in Washington State and compare that with the sea level down here in Southern California, there's an 8-foot difference between those two places. And here's San Francisco Bay. If we look at San Francisco area, we have a 4-foot difference between South Bay, which is higher, the red area, and Suisun Bay. So that's partially due to the fact that the water comes in and sloshes around and bumps around and reflects off of itself and reverberates off itself. But we definitely have the South Bay as an area that's of greatest concern. So let's take a look at what's happening in the South Bay. Here's an aerial photograph of the South Bay. Here's Route 101 here, all the way down. I think most everyone has been there. Here's Palo Alto. And if you know your geography well, here's Middlefield Road that goes through Palo Alto, right down here. So here's the bay, this blue area. And if we look at just a 100-year storm surge that would hit this area, no sea level rise at all yet, but a 100-year storm surge, look at what's going to happen to the bay water as we experience this 100-year storm surge. Boom. This blue area is where we would experience increased sea level from simply the 100-year storm surge. Now, if we had a 50-centimeter sea level rise on top of that, we would be out in this zone of light blue. And if we had a 100-year sea level rise, 100-centimeter sea level rise would be out in the yellow, and 150-centimeter sea level rise on top of this would be out in the red, just about to Middlefield Road, completely inundating Route 101. So you can see that we're in lowlands here, and we could be suffering really hard. So let's take a look at what's down in that area in the South Bay. It's Silicon Valley, of course. So we have Yahoo, we have Google, Intuit, Cisco Systems, Dell, all these big high-tech companies. And so I don't know if this were live, I'd ask the audience how many people have iPhones or iPads or iMacs or even invest in Apple. And most everyone raises their hand, but I think the people that have Apple products can be happy because Cupertino's headquarters is way down here and well protected from the likely inundation from the sea level rise or from storm surges. So count your lucky stars, invest in Apple. My son works for Apple, so you'll be helping him out too. Thanks. All right. In addition to the regular kinds of sea level rise that we also have the tides contributing to that. And we should understand that California has 2 high tides and 2 low tides each day. That's different around the world, but California has 2 highs and 2 lows each day. So let's look at one type of tide that occurs twice a month, and that's called the neap tides. That's when the sun is pulling gravitationally on the earth, sucking water one way, and the moon is perpendicular to that, pulling water through gravitational attraction the other way, perpendicular, and it's pretty much evens out around the earth. The spring tides are different. Spring tides are when the moon and the sun are both pulling in the same direction, and they pull the water through gravitational attraction out all the way out one side, and because of the spinning of the earth, the Coriolis effect, it's pouching out on the other side as well. Similarly, if we have the sun on one side and the moon on the other, it's basically the same gravitational attraction, a little bit less because it's the moon on the other side. But again, we have spring tides. So we have 2 spring tides and 2 neap tides each month. Now, the king tides are another type of tide or another phase of tide when the moon is closer to the earth in its elliptical orbit. So if we take a look at the moon in an elliptical orbit like this, it's not just circular around the earth. It has an elliptical orbit, and I exaggerated a little bit for effect. But now the moon is expressing its gravitational attraction more than it did when it was way out here, for example. So that occurs naturally, typically about 1 or 2 times a year. It occurs in January and some other times when the elliptical position of the moon is closest to the earth, and that lines up with the position of the sun and even some of the planets. When we have king tides, that's when we go to San Francisco and we see, even when there's no storms out there, these waves from the king tides are splashing over the sidewalks. And here's a guy in Sausalito that's riding his bike or motorcycle through the main drag in Sausalito. So this is serious. And here's all of the areas in this brilliant green that are being affected and that were affected in January of this year when we had king tides affecting the entire area around San Francisco Bay. So all of this is going to hinder our ability to use these establishments near the waterfront. And with the king tides, we get especially concerned about the runways at San Francisco International Airport, because they're right up, they're 6 feet or 6 feet to 10 feet above sea level. And when we start getting these king tides and sea level rise and storm surges, they're in trouble. So what they have proposed now is to put a 10-mile seawall all around the entire San Francisco International Airport to protect the runways from increasing sea levels. And because we have stronger storms and higher seas, we're now getting substantial beach erosion and cliff erosion from crumbling cliffs. So here's a diagram of California, and the red circles are those areas where we have the most cliff erosion and collapsing of seawall in California. So here's just some examples. Here's Isla Vista, California. This house isn't long for this world. One from Pacifica up here, another one not long for this world. Here's another one in Pacifica. Everything's eroding from there. These people are evacuating their place. And here's one in Lincoln City, Oregon. Similarly, there used to be a huge seawall here supported by all these concrete pillars. That's completely gone. So again, we have these cliff erosions and collapses happening because of more powerful storms and erosion of the cliffs from increased sea level. So we're not alone in all this. Atolls, which are coral reef islands, pretty round coral reef islands, they're only about 6 feet above sea level. These are affected as well. So if we look in some of these areas, this particular one in the Maldives in the Indian Ocean, I think overpopulated just a little bit. And yes, it is only 6 feet above sea level, and they're going to be in trouble here soon. Let's take a look at some of these island nations out in the South Pacific here. This is Papua New Guinea right here. Here's Australia. And the Carteret Islands have about 2,000 people. And because they're already being affected by this sea level rise and storms, they are planning to move their people to the mainland of Papua New Guinea. Tuvalu has about 10,000 residents, and they're planning to already moving some of their residents down to the South Island of New Zealand. Kiribati, or another way of pronouncing it is Kiribati, has 110,000, and they are moving their residents down to some of the high islands near Fiji. So it's not just the islands, though. Here's Shishmaref, Alaska, and they are on the coast, but unfortunately, the ice that normally is up in Alaska is all melting, and the storms now come right into their shorelines, and they have to move their villages back because they're getting inundated with storm surge. And these are the Inupiaq Eskimos in Shishmaref. And here's an example of what's happening in Shishmaref these days. Their houses are being tumbled over, and some of the local communities that are close to the ocean are getting wiped out. And if we look closer to home, here's a projection of what would happen in Miami. Could look like this if we just increase our temperatures by 2 degrees C, which is not unreasonable, because that's what we probably will end up with, was at least 2 degrees centigrade. Or we can take a look at this. We will have forced migration and many climate refugees situation where in sub-Saharan Africa, in South Asia, Latin America, and up to 140 million people will have to move because of sea level rise, inundating some of these areas. So just Florida has about 21 million people. Take a look and keep your eye on this area here in Florida, the lower part, and see what will happen with sea level rise by 2100. That's all gone. Now look at Shanghai, 26 million people. What will happen with sea level rise to Shanghai? Virtually gone, virtually gone. And where are all these 26 million people going to go? They're going to be fighting for a place to live, foods to eat, places to live. So just be aware that this is happening all over the world. And San Francisco, well, we won't have to worry about this for too long. I don't think this is going to happen in the near future, but I won't go into that one. So coastal storms, we are increasing our storms in the recent past and increasing what we call atmospheric rivers. Now, atmospheric rivers are typically what the weatherman on the TV talks about. It's basically an atmospheric river. These things are about 250 miles wide. They're a mile high, and they occur in the South Pacific area or mid-Pacific area around Hawaii. And I'm going to show you a superstorm that occurred. This is an atmospheric river storm that occurred in December of 2010. So here's the video clip. Here's Hawaii right here. And all of this tropical moisture is then streaming into California. And that particular storm, here's the counter right here, 19, 20, 21. That particular storm dumped 26 inches of rain in California on the coastal area and produced 17 feet of snow in the Sierra Nevada. So that's an enormous amount of liquid coming in. So we have another situation where these atmospheric river storms can be enormous. So the U.S. Geological Survey in 2010 did some simulation scenarios where they tried to track these 1 in 1,000 year events and what would happen in the future. So this is ARK, this is Atmospheric River 1000. So it's an atmospheric river that would occur 1 in 1,000 year event. So if we look at what's going to happen, they project that this would be a mega atmospheric river, 300 miles long by 20 miles wide. It would last for 45 days, dumping 10 feet of snow, or I'm sorry, 10 feet of rain, and estimated $725 billion in losses, mostly due to flooding and evacuation of 1.5 million people. And actually, they have recorded an arc storm, mega arc storm, in December of 1861 into January of 1862. That was an enormous storm that they have, proof records of. So what will happen in the future? And here's one down here that's showing how much atmospheric river water is flowing into California. We might not think that these 1 in 1,000 year storms or 1 in 500 year storms are happening or would happen, but here's 5 1 in 1,000 year flood events in the last couple months. This is all happening in the United States, so don't think that this isn't going to happen. And here's rain amounts: almost 1.5 inches of rain in Death Valley, where it never rains. 15 inches of rain in Dallas, 9 to 12 inches in Illinois, 9 to 10 inches in eastern Kentucky. All of these are rated as 1 in 1,000 year floods. What's happening here? What we need a different yardstick. We need a different metric to actually document these 1 in 500 year or 1 in 1,000 year storms. And we're just having so many of them that it's not realistic anymore. So the USGS, the U.S. Geological Survey, did a projection on the number of events that we would expect from these arc storm, 1 in 1,000 year storms, by 2055. We would expect 1 event by 2055, and we would be expecting 2 events by 2075. And these are all projections based on the type of climate we are having now. And if you want to see what would happen without climate change, this is the projection without climate change down here. So expect more of these mega arc storm flooding and events in the future. So when we get to 2055, you can say, hey, I knew that was going to happen. Okay, let's look at some of the ecological impacts that we're going to be facing, or that we are facing already. All of these species are along our coast, and we'll talk a little bit more about them. There's many different ecological communities along our coast. Some of them are kelp beds, some of them are eelgrass beds. Can't talk about them all, but both kelp beds and eelgrass beds are basically nursery grounds for many invertebrates and fishes. So they're really important. And these red stars indicate the locations of the major eelgrass beds in California, all the way up and down the coast. So we have high value ecological communities here, as well as many other places where there's kelp beds. So let's take an example from Humboldt Bay in Eureka. Here's Humboldt Bay. It's a very shallow bay. And then Humboldt Bay is the California's second eelgrass, second largest bay in California and marsh system. It has the largest eelgrass community. It's very shallow. It flushes completely twice a day, and it's highly productive. highly productive. This is kind of what the real eelgrass looks like. And let's take a peek at how complex it is. It has over 100 plant species, over 300 invertebrate species, over 100 fish species, 200 bird species, and hundreds of thousands of migrating waterfowl. It's an incredibly complex and productive place. So here's the sort of a simulation of what an eelgrass bed would look like with its component species. We have the eelgrass itself. We have things attached to the eelgrass, more different types of plants and animals. We have snails, we have crabs, we have fish, different types of fish, eels. We have marine mammals. We have migrating birds that are coming in and eating the eelgrass. We have some of these organisms in the pelagic zone, which is the swimming zone. We have some in the benthic zone, which is the bottom zone, with many organisms live, like the crabs on the bottom, or even some of the lobsters. And then we have the infaunal zone, which is in the sediments. There's many organisms like worms and clams that live in the sediments. So all of these species are dependent on this eelgrass community. And what we cannot avoid and leave out is the plankton. These plankton, the microscopic plants and microscopic animals, which provide the food for these tiny animals, which then pass up through the food chain, they're in there too. And we'll talk about these kinds of animals in a second. So we are here, located here along the coast of California, and this is what we call an upwelling zone. All these red areas in other countries are all upwelling zones as well. So we live in one of these upwelling zones where water from the deep ocean, and it's highly nutrient rich and it's very, very cold, comes up to the surface. When we have El Nino events slow winds and they also slow the upwelling. I'll talk to you about that and how it works right now. So let's assume that this is San Francisco down here at the top, and we're up in Oregon here. As the north winds blow down the coast, they actually curve and go out to sea because of the Coriolis effect and the spinning of the earth. And right here, you can see this arrow going out. So it takes the surface water, the winds take the surface water and push it out to sea. And when that happens, there's a void left here. And that void is taken up by upwelling water from the deep ocean. So when that cold, deep ocean water comes up to the surface, you got cold water coming up here, meeting warm air. That's how we get our fog, from those upwelling areas. And we also get the nutrient-rich water, which provides food for these phytoplankton, which is the microscopic plants of the ocean. And they provide food for the zooplankton, which are the microscopic animals in the water column, which provide food for small fish, which provide food for larger fish and onto marine mammals and birds, in forming a very productive, complex, diverse marine community. However, when we have an El Nino event, it stops these winds from happening, and the upwelling stops, and the nutrient-rich water stops, and everything stops going up the food chain, and we get a crash. And unfortunately, that is affecting birds and mammals. The bird populations crash. They don't breed those years. Marine mammal populations often don't breed because they don't have food to eat. The commercial and sport fisheries are down because we don't have the fish as abundantly. It affects entire ecosystems. So these El Nino events, which are lasting longer and longer in modern times, are affecting these entire ocean communities along our coast. Okay, we're going to get to the next topic here. OA, let's see. It is actually ocean acidification, a risky shell game to be sure. So I want you to put on your thinking caps now, because I'm going to give you a couple of scientific slides and I want you to understand this. So the ocean absorbs about 25% of all global carbon emissions. We talked about that before. And just like we talked before, here's carbon dioxide. We're up at 418 right now, 418 parts per million, way up here. And here's the increase that I showed you in the carbon dioxide increasing in our atmosphere. And when the carbon dioxide hits the surface of the ocean, that's the carbon dioxide atmosphere. And when it hits the carbon dioxide, the ocean surface, the carbon dioxide in the ocean goes up too, because it's being absorbed by the atmosphere or from the atmosphere. When that happens, when the carbon dioxide goes up in the ocean, we get a reverse effect of the pH. The pH goes down. And unfortunately, we have a reverse, an inverse relationship between pH and acidity. So when the ocean pH goes down, the acidity goes up. So that's a problem, because the more acidic the water, that lowers the saturation of calcium carbonate in the seawater. That's like limestone. The calcium carbonate is used by all organisms that are building shells in the ocean. And I'm going to show you a little more science here. So here's a little larvae with a shell, and it's progressing, growing up. And the first thing that there's two problems here. First, when carbon dioxide mixes with the seawater, we get this carbonic acid. And just like any other acid, it would start dissolving calcium carbonate, and it kills those larvae because they don't have any more shell and they die. So just simply the acid alone will affect the organisms. Now, the second problem is that as carbon dioxide mixes with water, it forms a carbonate ion, and the carbonate ion then produces two bicarbonate ions. You don't need to worry about those, just to realize that the carbonate ion is actually what the organisms use to build their shells. Whether they have an internal shell or an external shell, they use calcium carbonate ion to build their shells. However, because carbon dioxide mixing with water is stripping out those carbonate ions to make two bicarbonate ions, that is a problem. And therefore, the organisms that are depending on the carbonate ions to build their shells, it's not there anymore. So those are all being stripped out of the water column, and therefore the consumption of carbonate ions impedes the calcification of these shells for all those organisms that we love to eat. And since 1850, the world's oceans have experienced a 30% increase in acidity. That's because the carbon dioxide is mixing in that water. So all of these animals are ones that have external shells. Snails, oysters, the corals have internal shells. Abalone, sea stars, scallops, all of these are dependent on that bicarbonate ion, and they just don't get it as much. So their populations are suffering. So by the end of this century, it is predicted that the ocean surface will be more acidic than it has been in 400 million years. So this process is happening fast, and we need to stop it fast. So let's take a look at invasive species, another problem we have. So all of these species that I've shown on this particular slide are invasive species that have come up from tropical waters. The wahoo, great fishing, but not so good for our environment. Look at those big teeth there. We have the cardinal fish, we have largemouth blennies, we even have pufferfish from like the coral reef areas, spotted burrfish, another tropical species, and the whale shark, which is the biggest fish in the world, are all coming up north. Even these mola ocean sunfish, these are enormous species. And if you don't think these are landing on our shores, I found one of these molas on our beach up in Oregon. It's just phenomenal that these things are making their way up from the warm waters of the south, and now the warming waters of the north. They're spreading more and more, and they're even outcompeting some of the species that we have here. So be aware, look out for the mola next time you go swimming. How can we best plan for the future? Well, we need to plan for extreme variability, unpredictable changes, and resilience. And we need to think outside the box, really. So here's proposal number one. This is the solution we've devised for dealing with flooding caused by climate change. So maybe that's not going to get us all the way, but we can get at least some of those animals off. But we better do better than that if we're going to solve this problem. What are our solutions? Basically, we can't isolate California from the rest of the globe. California affects everything that's happening in the United States and vice versa, and everything that's happening in the global processes as well. So what happens in California, what we do in California in terms of our vehicles and carbon dioxide emissions is going to affect the United States and the global processes. What's happening in the global processes is coming to us in the form of impacts that we experience in California. So we can't isolate ourselves and be separate from the rest of the globe. We have to solve this problem as a unified entity with everyone else contributing. So what kind of solutions can we have? Well, we can have technological solutions, we can have legislative and political solutions, and we have some market-based solutions. So let's see how those can operate. So let's do the technological solutions first. We can develop further our renewable energy. Right now, we're using wind pretty effectively. We're also using solar and a lot of hydro in California. And we have geothermal up in Lake County. What we don't have much of is the wave operations, currents, and ocean thermal energy conversion and tidal. These are all in prototype modes, and we're not really utilizing them much. So it's mostly wind and solar right now, and hydro in California. So let's take a closer look at what's happening with this. We can't leave out nuclear. Even though it's not a renewable energy, we are going to need nuclear to get us through the time until we can technically and logistically improve the efficiency of these other types of energy production. And then maybe we can phase out of nuclear. But we're going to need that in the interim. So let's take a look at solar. Solar, photovoltaic cells for siding and tiles. We have the ability to use solar now much more so, but we better hurry up because the sun is only going to be shining for a predicted another 4.5 billion years. So we better get on this soon. The USA pretty much uses 3%, gets 3% of its energy from solar, but California gets 17%. We're moving more and more. Actually, we had 100% of our California's electrical needs serviced by solar earlier in the spring for 1 or 2 days. But that's just an anomaly because we didn't have much draw on the system. But we're getting better and better all the time. There's several different types of solar. And basically, the cost of photovoltaics is down 99% from the 1970s. And it's going down further and further now. We're going to be able to use solar much more so in the future. Here's another type of solar called heliostats or solar power towers. And each one of those little white dots is actually a mirror that collects sunlight. And that mirror reflects the sunlight back up into the top of this 400 or 500 foot tower where is stored molten salts. The molten salts absorb the heat and energy from these mirrors and can last through the night. And therefore, we don't have to have the sun shining at night in order to utilize them to drive the turbines that are going to produce electricity. So there have been some problems with some of these. These are found around the world, but we need to perfect them and make them more viable and more efficient. But this is another form of solar that we could put in our arsenal of optional renewable energies. Okay, wind. Over 5% of the world's energy supply comes from wind and 8% in California. So some of these may be familiar to you. This is in San Gorgonio Pass in Palm Springs, or the Altamont Pass, which is closer to home when you drive over 580 to Livermore. This is a wind turbine farm that produced 576 megawatts, and it was one of the oldest and at one time the largest wind turbine farm in the world. So we have plenty of wind turbines here producing electricity. We want more, and hopefully we'll get it. So some people are concerned, rightfully so, that wind turbines cause the death of birds. And no question about it, they do impact birds because evidently they can't see the blades very well. But there's been a lot of research on this, and they're starting to paint the blades in different configurations now. And it turns out that by painting them in certain configurations, they can get 72% fewer deaths from birds by manipulating the color scheme on these blades. So we're getting better in all ways in terms of getting better output and fewer deaths from those. So what can we do in terms of mitigation? We can do offshore wind. The Biden administration's goal is about 30 gigawatts nationally by the year 2030. And in May of last year, President Biden accelerated the implementation of California's offshore wind. The National Energy Renewable Laboratory is analyzing this right now on the California coast, and they feel like there's potential of up to 10 gigawatts from the California coast. And here's a map. Here's a wind map of California. So the darker the color, the higher the wind speeds. So we have a lot of high wind speeds up here near Eureka and Humboldt, and lower and some increase down here. But we have the entire coast that could be used. And so the Humboldt coast itself could be producing 1.6 gigawatts of electricity if we put those out there. And there was an assembly bill last year, California Assembly Bill AB 525. That was the Energy Offshore Wind Generation Bill, and submitted by David Chu. It became law in September of last year. And now they're required to do an assessment of the entire California coast by the end of this year, by December 31st of 22, to assess how much wind power we can expect here and how to potentially implement that. So we're moving forward with offshore wind, and this is kind of what it would look like. These are not bolted to the bottom of the ocean. These are tethered wind turbines. They have this technology already in process and in other locations around the world. These would collect energy from these turbines, and they would send it through a cable to shore. The one that is in the Humboldt area would be in Eureka, and then that would plug into the grid, the West Coast grid. So this is what's happening on our coast, and we sure hope that that can help in the long run. So the sources of electrical generation, just maybe summing up here, fossil fuels in the United States, still be using a lot of fossil fuels, 58% fossil fuels in the US, 47% in California. Nuclear, 19% in the US, 9% in California. We still have the Diablo Canyon plant. Wind, 9% and 8%, about similar in terms of US and California. Hydro, 7% in the rest of the country, and 11% in California. Of course, we have all those raging rivers. So 3% solar in the country, we have 17%. We're way ahead of the game on solar, and a little bit in each for biomass production. So let's take a look at other ways that we can improve our electrical systems. We can't produce everything from solar and wind. We need help. And grid scale battery systems are now coming online. And there's 7 different companies that are experimenting with grid scale battery systems. Tesla was the first to implement a grid scale battery system in 2017, and that was in South Australia. Tesla has other places where they're putting this in as well, in Moss Landing in 2020. And these provide an alternative, especially if we have the really hot days. They can provide stopgap measures of electricity, and they actually did in the last heat wave that we had. They were able to supplement the rest. They're discharged, but then they charge up again, and that's one of the next really important tools that we have in the toolbox is grid scale battery systems, and they're increasing the efficiency and the technology in those as well. And just for your interest, SMUD just announced that they just put in a 4 megawatt grid scale battery system, and over the next 8 years, they're hoping to have enough for 1,100 megawatt battery storage. This doesn't look pretty, but it's just like a big box. It doesn't have to look pretty, it just has to work. So SMUD's on it, they're preparing and they're going forward. All of these others is wind power engineering, SDG&E, all of these other places are adding these grid scale battery systems to their areas. And we also have what we call direct air capture, and capturing the CO2 out of the atmosphere. Remember, CO2 is going to stay there 500 to 1,000 years, so we need to get it out of that atmosphere. So Global Thermostat is the name of a company, and they're going to be they are sucking carbon dioxide out of the atmosphere. It's not exactly like putting it back into the smokestack, but it's pretty darn close. Here's a couple of prototype examples of the Global Thermostat company doing direct air capture. This is one in Menlo Park. Here's one in Huntsville, Alabama. And they literally suck air through these vents here, and they capture the carbon dioxide, put it into either a solid or a liquid form, and then they can do lots of other different types of things with it. They can produce cement They can produce liquid carbon dioxide for different types of things. And so we have a lot of these prototypes actually happening. So here's what, 6 or 7 of them right now. Some are all around the globe: Netherlands, Canada, Italy, and places in the United States. So again, technology is increasing, it's improving, we're gaining strides. Unfortunately, these direct air capture processes take a huge amount of energy. So when we can improve our wind and solar and other types of electrical production, we can use that electricity to drive these big, huge machines, these monster machines, to suck out carbon dioxide out of the atmosphere. So let's take a look at transportation. We have ways of solving this as well. Remember, cars in California are a menace here. 40% of the California carbon emissions come from transportation, only 20%, 28% in the US. So let's look at what's happening. Governor Newsom signed an executive order way back in September of 2020 that halts the sales of all new gasoline cars and trucks in California by 2035. And recently I believe it's been passed. In January 25th of last year, President Biden said that he wanted to convert the entire federal fleet to electric vehicles. That would be great. And look at this. In January of this year, General Motors said they will only sell zero-emission vehicles by the year 2035. That's amazing. And now over a dozen countries have committed to banning new gasoline automobiles over the next 1 to 2 decades. We are making progress, and we are making it pretty fast in my mind. Not only cars and trucks. Look at this, electric semis. This is a Tesla semi. You know about Elon Musk. He loves to have speed. Well, this semi cab can go 0 to 60 in 5 seconds. With the trailer, it'll take all of 20 seconds. So that's, he's up into the speed. But this kind of thing, this kind of semi, there's many companies that are actually making these semis now already, and they're going autonomous. So you might see one of these Tesla semis coming down the highway against you, and there won't be a driver in them. It'll all be autonomous, probably in 10 years. Going electrical, all electric, going from point A to point B. They charge up at point B and go back to point A, charge up at point A and go back to B. This is exactly the kind of thing that's needed in terms of increasing our technological advancement. And the US military is doing it as well. Much of their trucks and Jeeps and transport movers and even tanks are now being electrified, either up to hybrid or even fully electric. You imagine a fully electric tank sort of sneaking through the landscape. The enemy wouldn't even know we're there. And the last category I wanted to show you here was electric airplanes. Believe it or not, we are starting to have electric airplanes. The first electric airline came in December of 2019 from a British Columbia airline called Harbor Air. They run these beavers and otters into the backcountry to drop off fishermen and hunters, maybe 60, 80 miles, and then they pick them up when they're done, bring them back. So they're using all electric engines here already, but we're going to get past that. We believe that in the next 20 years, we're likely to have commercial airplanes carrying over 100 passengers. Airbus actually has a contest right now out to see who can build the most efficient electric airplane. And they're working on it rapidly. Again, transitioning, new technology, improving efficiency, all of these are happening at the same time. So let's look at the legislative and political solutions that we might have. Basically, putting a price on carbon is what we need to do in one way or another. And that price would be a price on each ton of carbon dioxide. And if we look at this, we know that every 3 barrels of oil is equal to 1 ton of carbon dioxide. Remember, we're producing millions of tons of carbon dioxide every day. So this is a map that's showing the different countries in green, and some of them about to do it in orange, that have already implemented some form of carbon pricing. And many of these countries are way ahead of the game. Unfortunately, there are some that aren't. So here's the top 5 carbon emitters in the world: China, the US in order: China, the US, India, Russia, and Japan. And unfortunately, these 3 with the red stars are those countries that do not have any kind of pricing on carbon yet. So here's the US here in Alaska, India, Russia, and unfortunately, they're not interested. Many of these countries are not interested. China actually does have one, and they are participating in this process to put a price on carbon. So hopefully these other countries who are in the orange, which are thinking about it or soon to implement, will also be doing that as well. So putting a price on carbon is one of the most effective ways that we can slow the price, slow the tide of carbon pollution. The more expensive carbon gets, the more expensive fossil fuels get, and the cheaper that alternative energy gets, the more alternative energy is going to be used, and just in a market-based solution. So back in 2015, Obama with the US led the Paris Climate Accord. They pulled together in 2016, they ratified that agreement, pulled together 196 countries to ratify the Paris Climate Accord. But unfortunately, 2017, we pulled out of the agreement, and I think all of you are aware of that. But in January of 21, the Biden administration put us back into the Paris Climate Accord, and we are operating with other countries to pull that off. And Biden has made climate change a central priority of his administration, which is great. So some other good news: nearly 1,500 governments worldwide have now declared climate emergencies, which then allow them to establish legislation to pass laws to then put a price on carbon, designate funding for fighting carbon pollution, and that's great. Also, over 6,000 companies and 7,000 cities in 133 countries are following the Paris Agreement protocols, which is fantastic. We are trying to, and we're making some great progress. And some market-based solutions. So companies are now divesting away from fossil fuels, and they're investing in renewables. So let's take a look at who's doing what. In January of 2020, BlackRock, which is the world's largest asset manager, $6.9 trillion in assets, and the biggest owner of fossil fuel companies, is now putting climate change and sustainability at the core of their investment strategy. I hope they're honest about that. They're moving investments away from coal, and they're ramping up pressure on polluters. In addition, the European Investment Bank, which is the largest public bank in the world, will stop lending money for fossil fuel projects. They've already allocated 8 billion euros to reduce carbon pollution. They've committed 1 trillion euros over the next decade to combat climate change. Amazing progress in the marketplace. Just incredible. And just last week, we heard that Yvon Chouinard, you probably have heard this already, who was the founder of Patagonia, he has given the entire value of Patagonia, $3 billion, to nonprofit trusts to address climate change. And get weepy just thinking about that. To accomplish this, how are we going to do this? We need to use all of those all those tools in the toolbox that I've been talking about, every single one of them. We need the chainsaw, the ratchet, we need the hammer, we need the wrenches, we need everything in this toolbox to do that. We are already making tremendous progress, but we need to do more, we need to do it faster, and we need to do it now. This is what I've been talking about in some of my presentations for a long time now. We can do this. The question is, can we do this, and do we have the political will to do this? That's the big question. Aha, August 16th, 2020. What happened in August 16th, 2020? Does anybody know? Anybody know? It was the IRA. No, it's not the Irish Republican Army, and it's not an independent retirement account. It's actually the Inflation Reduction Act. $369 billion was allocated for climate change. I know. I saw those people in the front row. They knew it. They knew that. That's how I put it up. So all I can say is, wow, 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 wow. This is fantastic. It's amazing. This is the largest single climate legislation ever passed. And it's just incredible. This is exponentially increasing climate. We have exponentially increasing climate events, and projections for the future is worsening. And we need to have all of the help and funding we can get. So let's take a look at what this bill gives us. $369 billion. And here's how it breaks out. Each one of these blocks is $1 billion. So we've got 369 of them kind of going off the screen. But we're going to allocate about $132 billion to wind, solar, and storage, battery storage update. And what that will do is it will incentivize the use of renewable energies and subsidies all the way down the line, building better, bigger and better grid scale battery systems, manufacturing of solar and wind, and manufacturing here in the US. That's going to help subsidize all of that. Next, we have advanced manufacturing, $37 billion. For that, we're bringing renewable manufacturing to the US. Next, we do need nuclear, $29 billion for nuclear. And that's to fill the gap that renewables cannot currently fill until we get the technology and the efficiency better in hand. Next, home energy improvements, $22 billion. That will upgrade appliances like your induction stove and some of the air conditioning units and all of the electrical things you have in your house. Put in solar, all kinds of things like that. $14 billion for home efficiency improvements. That will help us upgrade the HVAC systems, the heat pumps, insulation in your house, new windows, attic insulation, et cetera, et cetera. And another $12 billion for electric vehicles. You say, well, you can't do much with electric vehicles. Oh, we can. That will also extend the vehicle tax credits for vehicles another 10 years. Typically, when you have a tax credit for electric vehicle, it runs out after the first 200,000 units, and then you can't get that tax credit anymore. But they're going to extend those tax credits for new vehicles another 10 years. And the last group of blocks here is hundreds of other programs to help people. And associated with all of these other programs that are going on, we will be instituting wage and apprenticeship requirements so that we can have people, our own people, United States citizens, actually doing the work to bring up wind and solar production and wind and battery storage. So all of these things will be requiring that they meet requirements for apprenticeship and wage for people in the United States. So it's a fantastic program. It's going to help us immensely. So the bottom line is we've been funding, I'm sorry, I got some of these reversed here. Last 10 years, we've been spending about $220 billion a year on helping fight climate change. But with the Inflation Reduction Act and the CHIPS and Science Act, we're going to be now spending about $80 billion per year. Incredible amount of money, and it's all going to get used efficiently, hopefully, and productively. So let's take a look. Here's where we were back in 1800, and this is, again, carbon dioxide in tons, 1 billion, and this is for the United States, not for the world. The United States started out down at the zero end. So as we go towards 2005, our emissions, carbon dioxide emissions kept going up and up and up. So we start out here, and here we got 6 billion tons the United States pumped out during 2005. That was our highest emissions rate ever. However, now we've got, starting over here at 2005, this is the other half of the graph, we started going down. So here we started in 2005 with 6.6 billion tons of CO2 into the atmosphere for the United States. These are the historical emissions, and these are the modeled emissions. So here we're looking at the result of some of these legislative bills that have been passed. So I'm just going to go over here to where we are now. where we expect to be now. We're right here. I should put that up. Here we are now in 2020, but here's the projections of what we can do and what we're expected to do. If we just worked on frozen policies, we would end up with about 26% lower emissions below the 2005 level, which was up here at 6.6 by 2030. The current policy, including the bipartisan infrastructure law, will get us down a little bit more than that, 27% below 2005. However, the new IRA, the Inflation Reduction Act, will bring us 42% below 2005 levels. That's in the purple. And if the House Build Back Better Act was passed, it would have been very similar to the Senate Inflation Reduction Act. Would got us a little bit further, but not much. So be thankful for the IRA when you look at your congressman, that this is going to help us get out of this mess. And what we really need to be doing is to be on this pathway where we can reach 50% below the 2005 level to a net zero pathway. So we really want to be all the way down there and at the very latest get there by 2050. So this is where we want to be. This is where we are. So we still aren't there yet, and we still aren't even projecting there yet. We need more of the same. So your most critical actions are educate. Educate yourself on this issue, your kids and your tribe, those people you hang out with, your peeps. 2, try to communicate with your members of Congress. Each communication they receive, they consider to be representing 100 to 1,000 like-minded opinions from other individuals out there. So your vote, your opinion to make good on solving climate change issues is worthwhile, and it matters. It really matters. And the most important thing is to vote in all local, state, and national elections for those individuals who will work hard to solve this crisis. So we can solve this, we will solve this, and we just need to have you vote. And with that, I think we'll take some questions.
Okay, Tom, I've got a couple questions in chat. Gwen says, I was going to suggest that we might be living underground to avoid the heat, but with the mega storms and flooding, that won't work. Where do we go?
Good question. I don't think we have all the answers. We're going to be producing climate refugees in many parts of the world. Go to high ground. I would advise you not to buy property in Florida. That's basically my best guess right now. So I don't have all the answers. You can make the biggest difference by voting and contributing to those causes that are pushing hard to continue the funding for climate change relief.
Okay, Polly says, if California produces alternative energy, would we be able to keep it to ourselves, or would it be marketed by big companies to increase their profit margins?
Another good question. If we produce electricity in California, it goes into the Western grid. And so it goes all around. We get electricity from the Western grid, which is composed of all of the states in the West contributing. And unfortunately, we would like to think that even though California is producing a lot of solar, they're pumping it into the grid along with the other states which are burning a lot of coal. So, you know, we're working on it. It's getting better. We need to do more solar and wind and all those other forms of electrical production. But no, we're going to be producing power for other states as well, unless you want to buy your own nuclear power plant in your backyard, or your own solar cells on your roof, or your own wind turbine. All those you can keep to yourself. But you know, even then you would be pumping something back into the grid. But no, for the most part, if you're plugging into the grid, you're getting coal and gas and other forms of electrical production. But no, you won't be able to keep it to yourself unless you do those few things I mentioned.
Okay, Chris asks, what do you think about hydrogen fuel cells as an option for electric vehicles?
Hydrogen fuel cells are being studied now. They're in prototype mode. There's some hydrogen fuel cell outlets right now where you can fill up your hydrogen fuel cell car, but there's not very many. We're still in the prototype stage, I would say. They hold great potential, absolutely great potential, but the technology is not there to do them on a mass production basis yet. But I think we will see them. I think we will see hydrogen fuel cells come to the marketplace and be, competitive.
Are any American car companies doing hydrogen fuel cells?
I don't know the answer to that.
Yeah,
Sorry.
I think it seems to be mostly South Korea and Japan at this point, I think. Roger asks, what are the chances of the Sac State campus flooding?
I'd have to take an elevation, measurement, but Sacramento in general is the 25-foot elevation. And so you take your chances. You should get the elevation of your own home and see if we are going to go to the 100-foot level.
Well, I'm right across from Sac State and I'm at 26 feet, but they're doing a whole lot on the levee right now. They're putting all this stuff in the levee along Sac State and River and the next park up there, and where the Campus Common Golf Course. They're just putting billions giant rocks there. So Chris has another question. Do you think it's important for individuals to monitor their personal carbon footprint? And if so, what is the best way to measure it?
Okay, yes, I do, because I think we all need to have the same philosophy about saving our planet, and that's everyone can contribute. And the more we contribute individually, and involve ourselves with all of these programs and vote in the right way, that's all part of the same philosophy that we should carry with us. And in terms of the, what was the second part of that?
What's the best way to measure it? How do we know?
You can go online and get the carbon counter. There's a way that you can measure how much electricity, how much carbon you're producing based on the automobile you have, how much kilowatt hours you have, what electric company you use, and many different factors that will tell you how much carbon you're outputting.
Okay, and okay, Diane has mostly a comment here. We must remember we're all in this together throughout the world. So Kitty asks, how effective is planting more trees to reduce CO2?
Oh, yeah. Planting more trees is definitely helpful. Trees are very effective consumers of carbon dioxide, but it's not the end all. It will help, but it's not. Many people think, okay, we just need to plant, billions and billions of trees. Well, there's not enough landscape to plant enough trees for us, available to plant enough trees to make a difference. The biggest difference that we can make globally is to put a price on carbon. We've proved that through multiple investigations, and so that feeds into the legislative end of things. And the more that we can convince Congress, all the legislatures of all the countries in the world to support that, the faster we're going to get there. There's a lot of pushback from the fossil fuel industry. However, the fossil fuel industry people are not stupid. I mean, they're smart cookies. They are also developing alternative energy programs themselves. Shell is doing a lot of that right now, and they're advertising it. I suspect every one of those fossil fuel companies is doing that with their engineers behind the scenes, not necessarily advertising it, but they might all start popping up as well.
And also, while people here are planting a few trees, that thousands and millions of trees are being ripped out of the Amazon by greedy companies down there.
Exactly.
Yeah.
So we're fighting a losing battle there until we get rid of Bolsonaro.
Okay, and Karen
I see Lee has his hand up.
Oh, yes. Lee, why don't you unmute yourself and ask your question?
That's a good question. All of the technologies that you were describing seem like they would lower the output of carbon dioxide, but you still have the problem that it's simply the amount in the atmosphere that's creating that blanket around the Earth is still going to be there for 500 to 1,000 years. So is there anything, at least, in other words, it won't get worse as quickly. but that doesn't necessarily mean it's going to get materially better than the events that we're already experiencing. So is
Yeah.
there anything in the works that would actually get some of this carbon dioxide out of the ocean and out of the atmosphere?
Right. Yes. And I mentioned the atmospheric reduction with all of the machines that we're making now that pull carbon dioxide out of the air. We don't have those functional yet, or in the marketplace, but there's other ways that we can pull carbon dioxide out of the atmosphere. We certainly are doing it with trees, but that's not going to do it alone. We also have different types of soil amendments that suck up a huge amount of carbon dioxide, and it's a matter of almost like planting crops. If you plant and seed these fields with the right kinds of minerals, those will be taking up carbon dioxide as well. So I didn't have time to go over many of the other forms of carbon dioxide removal, but there's many different types of other forms of carbon removal that we can use. And again, they're all in the prototype stage. UC Davis was doing some of this in terms of the farming of soils to suck up carbon dioxide as well. So we have them out there. It's just a matter of moving as fast as we possibly can, and as fast as we possibly can, not to add to it as well. So yeah, there's other options. Thanks for the question.
Okay, Karen asks, with the push for electric vehicles, will the power grid be able to handle the demand for charging?
Yeah, I mean, the electric vehicle companies are not going to go anywhere unless they have the charging systems there. And right now, Tesla has the greatest number of chargers out there. And Tesla is now planning to open up their chargers for other types of other models and makes of electric cars too. So we're getting there, and we just need to do more and more and better. Again, the same story.
She's kind of asking about the power grid itself. Is that going to be able to handle that? We don't know, I don't think. I don't
know much about the power grid. So I assume that if they're going to build it, they're going to have to make it work. But I'm not familiar with that.
Okay, someone named Cindy, a suspicious name, I think. Can you put the carbon counter into the chat or send it? Or actually, Tom, you could send it to me and I can send it out when I send the recording tomorrow.
All right. I also have on my website, I have a 50 things you can do as an individual to lower your carbon footprint.
Oh, send me the link to that too, and I'll include it in the message tomorrow.
Will do.
Okay. Someone strangely named Samsung asks, what is your projection for fusion?
Fusion, I don't think that we're going to get there very soon. Last week we had the presentation by Jerry Glasser, and if we come up with cold fusion or any other kind of fusion, it'll be a miracle, and that'll really change the whole nature of all of our efforts in terms of electricity.
Okay, that's all the questions I'm seeing right now, either in the chat or the hands.
Okay.
So we'd really like to thank you for doing this.